Okay, last time, if you remember, we looked at Thomson's experiment, which gave us a value of E over m, okay? And that's obviously not a very satisfactory situation because, of course, you don't know E and you don't know m, you just know the ratio, okay? What's called the specific charge for the electron, okay? What we're going to do today is have a look at the obvious experiment to come next, which is, can we do an experiment which will unpick those two things, which will allow us to get an actual value for E, and therefore an actual value for n, okay? And this experiment is known as Millikan's oil drop experiment, okay? It's the second experiment you're supposed to know about as part of the turning points thing. And it's designed to give us a value for E, the charge on the electron. Not E over m, but E itself. Alright? Now, first thing to do, I think, is to get a drawing of the equipment, and it looks something like this. Okay? Okay, in lots of exam questions, I don't bother with the top bit, how you generate the oil drop, because that's not really relevant, but we'll include it anyway. It's the bottom bit here where all the business is done, all the stuff's worked out. So you may see this in exam questions with the top bit missing. It's just literally two metal plates with a gap in to allow the oil drops to come through. Just make that one center. Okay, now, first of all, we need to generate our oil drops. So, you have some oil, and you have a squirty thing, a bit like a perfume diffuser, something that's just going to take the liquid and spread it out in a fine spray, okay? And that's the first part of the experiment. So as you might guess from the title, the first thing to do is to produce some drops of oil, and that's what the top half is for. So it's basically just like a perfume diffuser. You squirt it, and out comes, in this case, droplets of oil, and they fill up the top section. Okay? And under the power of gravity, some of them are going to fall down through the hole. Okay? Now, the key thing to understand about Millikan's experiment is it's done in two stages, all right? In two quite different stages, and you'll see why that is in just a moment, all right? So the first thing we're going to do is we're going to allow the drops to fall just under gravity, okay? Now, how are we going to take any measurements with them? Well, the first thing you need is some sort of microscope, somewhere to put your arm. Okay, so there's a microscope of some kind, which will allow him to see them, because obviously they're very, very small. So in the side of the equipment, there's a hole with a microscope looking through, and Thompson, or anybody who wants to have a look, can see the drops, and on the opposite wall, you would have, or somewhere, you'd have some sort of scale, all right? So he can time how long it takes the drops to cover particular distances, okay? Now, these two metal plates are going to be linked to a very large voltage, okay? We're not going to do that at the moment, okay? So the bottom half of the equipment is two metal plates which can be charged up with an electric, to produce an electric field, okay? There's also going to be a source of X-rays, and that's going to be used to ionise the drops, okay? But these two things are not used in the first stage. So, in the first stage, the X-rays, which ionise the drops, make them charged, that's not there, okay? That's not turned on. And also, the E field is not turned on, all right? So the first part of Millikan's experiment is done with no electric field in the bottom and no X-rays to ionise the drops. The drops are uncharged, they're neutral, and they fall through under gravity, okay? Now, what we basically do then is we watch the oil drops, and what the oil drops do, of course, is to reach a terminal velocity, okay? As they come through the plate, they're accelerating, but being very, very, very tiny and travelling through something like air, as you know, teeny tiny things have a very low terminal velocity. They're going to hit that point where they're not going to speed up anymore fairly quickly. So as they fall past here, Thomson can see them falling, and he can say, right, start the stop clock, and he could measure how quickly they travel from one place to the other and work out the terminal velocity. Okay? So here the drops are falling under gravity, no ionising, no electric field, just falling under gravity and reaching terminal velocity, which we measure. Okay? Now, let's think a little bit about the physics of our drop in this situation. Here's our oil drop. Okay? The force pulling it downwards is obviously the force of gravity, m times g. And what's going to be the force going the other way? If it's going to reach terminal velocity, we've got to have those forces balanced. Terminal velocity, there's no acceleration, is there? So the total force must be zero. Air resistance or drag. Okay? So there's going to be a force of drag, because it's a moving object in the air. Okay? There's going to be a drag force in the opposite direction. Okay? Now, drag forces are not something we tend to have equations on at A level, and that's partly because they're generally horrifically complicated. If you're building a new Formula 1 car, you may well use some clever design software that can model how the air might flow over the thing, but ultimately, even though you spent millions on people sitting at computers doing that kind of thing, you then put the car into wind tunnel, all right? And all the top Formula 1 teams make use of wind tunnels, and that speaks volumes about how accurately can they predict the drag force on a new car using physics, using equations, using computer modelling, up to a point, but if they want to be sure they're going to get it right, they still put them in a wind tunnel, okay? Drag forces, anything to do with liquids moving, anything like that, if you go on to further course in science and stuff like that, if anybody talks to you about a course involving liquids moving, hydrodynamics or something like that, just turn around and run, all right? The maths will be horrendous, okay? The equations for the friction, the drag forces on this pen as it falls are probably too complicated to write down on one whiteboard, okay? Drag force equations are generally incredibly complicated, okay? However, if I said to you, well, we're going to be bold today, we're actually going to have a go at an equation for drag, what's the simplest shape you could imagine? It would be a sphere, wouldn't it? So, we're going to have a go at writing down the drag force for a sphere. Anything more complicated than that, we're just not going to do, okay? Now, the good news is there is an equation for drag forces for things which are spheres, okay? And the drag force there is a strange looking equation. That's the equation for the drag forces on a sphere, okay? 6 pi, because it's round, okay? R, what do you think R is? It's the radius of the drop, isn't it? R is the, if I hadn't coloured it in, that would be more helpful. R is the radius of the drop. The bigger the drop, the bigger the drag force, no surprises there, okay? V, pretty obviously, is the velocity at which it's moving, okay? Eta is a funny looking thing. It's the Greek letter eta. It's like a lowercase n, but with a sort of a curly front. So it's like an n, but you put a bit of extra on the front there, okay? Eta is known as the viscosity, okay? And in this case, it'll be the viscosity of the thing it's falling through, which is air, okay? So eta is a constant. If you drop the same sphere in golden syrup or something, you're going to get completely different drag forces, okay? So we're not surprised to find something to do with the material you're falling through, something to do with the size of the sphere, and something to do with how fast it's going. If I'd asked you for those things earlier, I'm sure you could have told me they're going to affect it, okay? Now, this very grand piece of physics is known as Stokes' law, all right? And Stokes very bravely set out to basically work out an equation for the drag force on a sphere, okay? And I promise you, anything more complicated than that, you don't want to know about. Anything even as complicated as a pen, just horrendous equations. But the good news is Millikan's doing his experiment on oil drops, which are little spheres, and we can therefore write down an equation for the drag. That's probably the only time we're going to do that in the whole of A-level physics, okay? Now, it's then pretty easy, because 6 pi eta RV has got to equal mg, all right? If the thing's falling at terminal velocity, it's neither speeding up nor slowing down, the drag force and the weight must be the same, okay? Now, again, this is real practical physics. This is physics no one's ever done before. If you're actually doing this experiment, what things can you actually measure and what things are you going to be able to work out? I don't know why it's doing that, I wish it wouldn't. 6 pi we're fine with. Eta you can look up in a data book. Okay. V, remember that's the whole point of this travelling microscope and this scale, is that he can estimate, I suppose is the best way to say it, he can have a go at measuring the velocity. Okay. G we know. The problem is we seem to have two things we don't know. We don't know the radius of the drop, and that would be quite difficult to measure because they are very, very small and moving. It's going to be extremely difficult to try and estimate with the microscope. And also the mass of the drops we don't know. Okay? One of the reasons for using a diffuser here is we are hoping, this is pretty much what the whole experiment hinges on, is the drops are all pretty much the same size. Okay? Anyway, we've still got this problem, that R and M, but there's a way of breaking M down, isn't there? If you think about it, the mass of the drop is going to be the density of oil times the volume. Alright? The mass of the drop will be the density of the oil times the volume, and we know the volume of a sphere, it's our old friend 4/3 pi r cubed, do you remember that? Volume of a sphere? So this side is going to be the density of oil times 4/3 pi r cubed times G. So actually there's our equation. 6 pi eta RV equals 4/3 pi r cubed rho, density of the oil, times G. Okay? Now if you look at it, what's the only thing we don't know? Are you with me? Where are we? Yeah, it's R, isn't it? There's only actually one thing we don't know in this equation. 6 pi eta RV and 4/3 pi r cubed rho times G. The only thing in all that, it's a very complicated looking equation, but the upshot of it is, using this we can work out R. Okay? If I'm a physics examiner, I'm going to be less bothered that you can plough through the maths particularly, though I might give you some values to go through. But this is the first point, alright? The first part of the experiment, you do it with the field turned off, with the X-rays turned off, and you use the terminal velocity of the drops in air to determine R. Okay? And that's the first part of Millikan's oil drop experiment, and there are two. Step 2, pretty obviously, you turn the X-rays on, and you turn the E field on. So you turn the big voltage on. Okay? Now, as the drops fall through, now they're hit by a beam of X-rays. And what the X-rays will do is to ionise them and will make them negative. Okay? So now, it's a bit difficult to draw negative dots, but there you go. Can you draw some negative oil drops? The oil drops are now charged. They've been zapped by X-rays as soon as they reach the second half of the equipment, and that means you've now got charged oil drops. They've all got some negative charge. It would be nice if they all had exactly one unit, if they were all singly ionised, in other words, they all just gained one electron. But if you want to be quite accurate, what you need to do is to show different amounts of minus. The problem is they're going to come through with different amounts of ionisation. Millikan doesn't know this yet, although it looks as though he had a fairly good idea. Clearly some of them will have gained one electron, some of them will have gained 2 electrons, some will have gained 3. They're all coming through with different amounts of ionisation, which is slightly annoying. Okay? Now what we do is we adjust this voltage. Okay? So this voltage you can adjust. So you sit there with your eye at the microscope looking through at the dots, and you've got to control. You control the voltage that's being applied. Look at the way it's being done. The top plate is plus, and the bottom plate is minus. Very important. And what you do is you vary. I think actually in the original experiment they just earthed the bottom one. Doesn't matter. The point is the top one is plus relative to the bottom. Okay? And what that means is you can use it to apply an upward force. So let's think about our drop again. Again, downwards we've got mg. But now we've turned the E field on, so we've now got upwards, we've got some sort of electric force. Okay, we've got some sort of electrostatic force pulling it upwards, and of course we know that. Same as in the other experiments, it's Q times E. Okay? Now, what you do now is you adjust the voltage, you pick a drop, because the trouble is you can't do it with all of them at the same time. So you watch with your microscope, you find a likely looking drop, and as it comes down, you increase the voltage. What will that do? I'm watching a drop falling, I'm increasing the voltage. What will happen? It'll slow down. If I keep increasing, go back up. If I drop it back down again, you get it to stay still. And that is much easier to say than to do. It's a right nuisance to do. But in principle, what you do is you get the drop to stand still. Okay? You pick one drop in particular. We don't know how much charge this one's got. It could be -1e, it could be -2, -3. You just pick one. It's quite difficult because other drops with different charges won't stop. So you have to pick one and you adjust the voltage. If it's too big, you'll send it back up. If the voltage is too small, it'll start to fall. You adjust the voltage until this thing has stopped. And this is important because in the second part of Millikan's experiment, it's different to the first one, all right? In the first one, you let them fall and measure their terminal velocity. In the second one, you stop them. You use the electric field to hold them up, okay? Now what we've got, nice simple equation by the look of it, QE is M times G. All right, it's as simple as that. Why don't we bother with Stokes' law and the drag forces? Yeah, because it's not moving, is it? All right. In the second part of the experiment, and again, here's the physics. This is the bit that's more likely to be examined, the physics of what's going on, not just the equations. In the second part, because you stop the drops to take your measurements, you don't need to worry about drag forces because when it stops, it's not moving. Okay? So the equilibrium here is this. All right? In the first one, you let them fall at a constant velocity. mg is equal to Stokes' law, 6 pi to RV. In the second one, you stop them so that mg is equal to your stopping force, which is produced by the electric field. Okay? Now, this is what we're after. This is what we want. Look here, we've got Q. I think you can see what's going to happen though. We've also got M. Well, let's go through what we can measure. We can measure E. We can look at what voltage. So what voltage just stopped our drop rather. What voltage exactly stopped it? And what distance is this? We can obviously work out E from that. G we know. Okay. Looks like we've got the problem again. Just before we started, we talked about the problem of Thomson's experiment. Whatever he did, he got Q over M. If he'd done it electrically, magnetically, he would always have his unknown, would be Q over M. It looks like we've got the same problem here, but let's do the same thing as we did before. The mass of the drop is 4/3 pi r cubed, that's the volume of the drop, times the density of oil. Okay? Mass is volume times density, so that's the formula for the mass. And if you look in here, the thing we don't know, of course, is R, but we do because we know R from part 1. All right. QE equals 4/3 pi r cubed times rho times G. In this equation, it looks like you've got two things. You don't know Q and you don't know R. And if you just did the second part on its own, it's no different to Thomson's experiment. He's making charged things do stuff due to electric fields. It doesn't matter how you do it, whether you do it that way, whether you do it that way. If you make charged things do stuff with electric fields, what they do will depend on Q and M. But now, with part 1 in place, we've actually got R. We know what R is from the previous section, okay? Section 1 gives the value for R. Now, if we know R, we know rho and we know G, obviously. You can see QE equals 4/3 pi r cubed rho G. The only thing we don't know is Q. And from this, of course, he gets his famous value for the charge on the electron. We can now measure, stroke estimate, the charge on one of those drops, okay? QE equals mg, but we know M because we know the radius of the drop from part 1. Okay? So these are the two stages. Here's the physics underneath all this maths. Turn everything off and let them fall. Balance Stokes' law with gravity to get R. Turn the field on and ionise them. get them to stay in position, and then balance the electric forces with gravity. Of course, now you know this one because you worked out R in the first part. Okay? Now, in principle, this is what the textbook tells you. Millikan, to his credit, did this experiment many, many times to take averages and stuff like that, and he worked out his values of Q in coulombs, and he got things like 1.6 times 10 to the minus 19, 3.2, 4.8, 1.6, 3.2, 4.8, 1.6, 3.2. Are you with me? He did loads and loads and loads of drops, and he estimated the charge on them. He looked at those values for charge on the drops and said, well, they all seem to be multiples of the 1.6, all right? All the charges, some of them have clearly got more charge and less charge, but the ones that have more charge always seem to be either twice that, or 3 times that, or 4 times that. I don't seem to get values which are sort of in between, okay? And from that, he deduced that the charge on the electron, the fundamental unit of electric charge, is 1.6 times 10 to the minus 19 coulombs, okay? And obviously from that, with Thomson's value of E over m, you can then get a value for the mass of the electron, which blew people's minds because, of course, it's 10 to the minus 31, I think it is, isn't it? 9.11. Yeah? So again, a massive experiment in particle physics. This is arguably the second experiment in particle physics. And by virtue of this, we now know the fundamental unit of electric charge, the charge on the electron, and from that we can work out the incredibly small. Remember at this time, 1910s, something like that, people are still arguing about atoms. There are still respected scientists who don't accept the idea of atoms. They say it's either just a pointless thing because they're so small we're never going to see them, or they just don't think they exist at all. Okay? And this is just an immense result, the mass of the electron at minus 31. It's probably worth saying this has attracted a fair amount of debate. Since the experiment, many people have gone back to Millikan's original results, and they don't look like this. They have things like to which Millikan didn't publish them. So it's fair to say I think Millikan had a fair idea of what he was hoping to find. And he did get, and you do it because it's a pick of an experiment to do, you do get values that are clearly just rubbish, you clearly just made a mistake or something, and he sort of lost them. So this is Millikan's experiment, all right? In the exam, be clear about the physics. Are you with me? It's what he's actually doing. I know the equations look horrible, but it's the physics of what's going on, the two-stage nature, one to get R, one to get a value for E, okay? But this is the second experiment in turning points, as you can see, and the logical successor to Thomson's experiment for E over M. We now have a value that will give us E and therefore M on its own. Okay?